Mr. B. Dhanasegar is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science, and we are studying the subject that is theory of computation as far as this episode is concerned. I will just start with what we have seen in the previous lecture. So, we have seen that the regular languages are there, and it is going to be the basic class of language as far as the Chomsky hierarchy is concerned. And then we have seen that there is a class of language which is not going to be regular. So, if it is not going to be regular, then how do you prove this language is going to be not regular? So, we have seen that the pumping lemma could be used for proving the languages as not regular. So, if the language becomes regular, then it is okay, we will be having your finite automata or the regular expressions, they can be that is obtained. But if the language is not going to be regular, then we must prove that the language is not regular, which means we cannot find out any finite automata or regular expression for the language. So, it requires some kind of tool for proving the language is not regular. So, it is with the help of the pumping lemma we are proving the language is going to be not regular language. As far as this episode is concerned, we are having there is some examples for non-regular languages. There is the languages for which there is no question of having any finite automata or the regular expressions. Then followed by that we have there is closure properties of the regular languages. That is, how do we make use of the various operators or the properties in order to build very complex regular expressions, so that we will be able to recognize even more that is bigger languages than the basic primitives. So, we just start with what are the non-regular languages, some examples for the non-regular languages, and here we have some of the non-regular languages. The first one we are seeing is a power n followed by b power n. Already I talked about this, that your languages, suppose if they need some memory for the recognition of it, then the languages are not coming into the regular languages. As far as this particular string is concerned, we find the number of A's we are recognizing from the first part must be remembered in order to recognize the number of B's. So, if I am recognizing 5 number of A's, then I should recognize exactly 5 number of B's. So, without remembering how many A's I have recognized so far, it is not possible to recognize the same number of B's. So, memory is strictly needed. The second part we find a power m followed by b power k, where we do not find out any direct relationship in between this m and n in terms of the equality, but here the condition is the number of symbols available in the first part, that is your number of E's must be greater than the number of B's. That is why we are having the condition m greater than n. So, to satisfy this constraint, once again we should know the number of A's we have recognized. So, both the problems require some memory for recognizing the strings of this form, whereas in the case of third one we need to recognize the entire string itself, not just the count. So, just recognize what is the first part of the string, then we have to recognize the W reverse, it means exactly the reverse of the first part. So, once again it requires the remembrance of, or we have to store the string, that is W in some memory, so that we will be able to verify the second part of the string is exactly the reverse of that or not. And the fourth one is going to be that is your x, and the condition is the number of A's and the number of B's available in the string must be same. So, equal number of A's and B's, but not in the same order, but it could be in any order. And the last one we find that is your a power n followed by b, once again a power m. We find that a is available in two places with the n number of A's first, then followed by m number of B's separated by B's. But whereas in the case of the last component of your a, we are having n plus m number of A's. So, without remembering how many A's in the first part plus the number of A's in the second part, we can't recognize or remember equal number of, that is same number of A's in the third part. So, all these problems are all in need of some memory for the recognition of those strings, but we do not have any memory as far as the finite automata is concerned. We can just find out what is the previous state from where from we have reached the current state. So, we can understand that what is the previous symbol recognized rather than just knowing what are all the previous symbols recognized from the starting state to the current state. So, that is the reason why we need memory for recognizing all these strings, and the memory could be found only in the push down automata, which is a tool or a device used for recognizing only the context free languages, but not the regular languages. So, we can say that these kind of languages are not coming under the regular languages, because of we cannot construct finite automata for them. And if you find that the languages could be recognized with the help of a stack, then they will be coming under the context free languages, and if it could be recognized with the help of a Turing machine, then they will be if you are coming under the linear bounded automata, then they will be coming under the your context sensitive languages, and if they can be recognized with the help of a Turing machine, then they will come under either recursively enumerable or it is going to be recursive languages. The next is the closure properties for regular languages. The closure properties, actually we have to start with what are all the basic operators supported by the languages of the regular classes. Already we have seen the operators like the union, then it is going to be the concatenation, then closure. For all these we have seen operators, like as far as union is concerned, it is going to be the plus operation, and the concatenation, it is either the presence of a dot or simply writing the first pattern followed by the second pattern. As far as a closure is concerned, we have used that is your star for the repetition. So, these are the basic operators which are already supported by the regular languages. Now, if you want to build more complicated regular expressions or more bigger regular expressions, so that we will be able to recognize even wider, that is classes of languages which are still coming under the regular, then we should understand what are all the properties accepted by the regular languages or regular expressions. So, if you are saying an operator sum x, then if the operator accepts the regular languages or regular operation, then we can say that the new expression which you are finding or which you are getting by applying this operator will also be a regular one. Just for example, we can say it is complement. You define an operator for complement, and the complement of a regular expression, we have to find out whether it is also going to be a regular or not. That is the complement of a regular language, whether it is going to be a complement or regular language or not. So, for that we should understand whether this complement operator is already supported by the regular languages or not. If it is supported, then the complement regular expression is also going to be a regular expression defining a regular language. But if it is an operator which is not supported by the regular or regular languages or regular expressions, then the new language is not going to be a regular language. Now, we should understand what are all the operators supported by the regular languages or the class of language called regular or regular set. So, here we have the list of that is regular languages. So, the regular there is operators. The first one is the union. So, union of two regular languages is going to be a regular language, and the second one is going to be the intersection of two regular languages. So, given a language R and another language S, the language obtained by the intersection of R and S is also going to be a regular language. That is the meaning of the intersection operation. And the next one is the complement of a regular language. The complement of a single, that is a language, that is a regular language, it is going to be the that is your unary operation. But whereas in the previous two cases, they are all the binary cases. The next one is difference of two regular languages. Given a language R and another language S, so what will happen if it is going to be R minus S? So, that is also accepted by this closure properties or your regular languages. The next one is going to be the reversal of a regular language, a string that is reading from that is left to right, and if you are having the same string when we are reading from the right to left, so what will happen for the language? Can you construct an automata for that language or not? That is also possible. So, we call that language is also regular. Then another one is the closure. It is going to be 0 or more number of times of a language. That is closure of a regular language. Normally, we will be using the asterisk operation in order to recognize or in order to define languages with the help of the closure. It means 0 or more number of times of any given language. So, the complement, reversal, closure, unary operations and the others are all that is binary operations. So, now we have to see that is how these properties are all proved. The first one is we have to find out whether the union is going to be accepted by the regular languages or not. As I described, that is union is going to be a binary operation. It requires two regular languages or two regular expressions. Given two regular expressions, then we will be having two finite automata. So, now we have to go for finding the union of these two regular expressions. To give another single regular expression describing the language obtained by the union of the language accepted by the regular expression R and the language accepted by the regular expression S. But the condition is we must have a single starting point, and finally, we are expecting that the final state should also be a single state or unique state. So, in that case we need to combine both automata, that is the automata meant for regular expression R and the automata meant for regular expression S with a unique starting state and a single final state. So, what are all the various transitions required for just combining this to form a new automata? Definitely every transition available in the automata meant for R and the transitions meant for the automata that is S must be available in the final automata, because we need to take a path either through the first automata or through a second automata in order to recognize a string either from the first automata or from the second automata. So, all the transitions must be copied. In addition with that, we need to form 4 new transitions. So, these transitions are actually making the connection in between the automata meant for R and automata meant for S, and how they are connected in order to form a new automata which recognizes the language that is union of R and S. The process is completely described here. First you are given that is two languages L1 and another one is going to be that is L2, and both are assumed to be that is regular. Then we assume that there exist deterministic finite automatas, that is one for that is L1 and another one for L2. The language L1 is recognized by finite automata M1, which is having its own components, set of states, input alphabet, transitions, starting state and the set of final states. Then we have an automata for L2, because that is also regular. The set of all states, it is going to be Q2 and it is going to have its own alphabet. So, the alphabet not necessarily be same for both L1 and L2, they can be completely even disjoint languages. So, we are having sigma 2 as the alphabet for the second automata. Then there may be any number of transitions, that is del 2, the starting state is going to be different one, it is going to be Q2 for that is M2, and we will be having some set of final states that is going to be F2. But what is the condition there? That is your L of M1 should be L1 and L of M2 must be equal to L2. So, now we have to form or we have to find out how do we construct an automata for the language that is meant for L1 union L2, that is a string either in L1 or in L2, that is what we wanted to have. So, here there is the automata M1 and M2 are deterministic, but when you are constructing the automata meant for L1 union L2, by the construction what we are following here, we will be getting only a non-deterministic finite automata. But that is not going to be an issue at all, because for every non-deterministic finite automata, we will be having an equivalent deterministic finite automata which could be obtained by using the subset state construction algorithm. So, you just construct an NFA that is M and which is going to have the set of all states Q, the alphabet that is going to be sigma, and then we are having some number of transitions that is del, a new starting state Q and a set of final states. So, now how do you obtain all these components? That is going to be the construction of union of two automata M1 and M2. The first one is how do we construct that is the number of states. As far as number of states are concerned, every state from M1 and every state from M2 should be available in the new set of states of the newly constructed automata, that is M. In addition with that, we want to have a new starting state and a new final state. So, we will be having that is Q1 union Q2, and here we are seeing that is going to be your that is q, that is going to be a new starting state. As far as this construction is concerned, the final states are taken from the union of final states of the first automata and the final states of the second automata. So, it is not going to be a new state here. So, suppose if you are including a new state, there is some f as the final state of the new automata, then that should also be included as part of the union. So, you will be going for q is the q1 union q2 union, that is q union f. So, every state available in the first automata, every state available in the second automata, plus the state which is meant for the starting state, and if needed we can go for an even new final state. So, this is what the entire set of states available in the union automata or the resulting automata is concerned. And now we have to consider, that is what is going to be the alphabet, what is set of all transitions, and how do you find out the final state. So, all those things we shall see after a short break. Welcome back. We are seeing the state construction for the union automata, how the finite automata states are all evaluated when you are taking the union of two finite automata. And the next one we have to see is how the finite, that is your resulting automata alphabet is evaluated. That is, given two automata, we have to find out the union of both. Now, we have to find out what will be the alphabet for the new automata which is obtained by the union of both the automata. So, we know that a string is going to be there as far as your first automata is concerned, or it is going to be there in the second automata. If it is there in the first automata, then it is formed from sigma 1 star, and if it is from the second automata, then we are forming it from sigma 2 star. So, now in the resulting automata, we may have a string either from the first automata or from the second one. So, unless otherwise we make, that is your alphabet as the union of sigma 1 and sigma 2, we can't recognize any string from the new automata, that is m. So, obviously it becomes, your sigma becomes any symbol from sigma 1 or from sigma 2. So, how do you obtain that? It is just by taking the union of sigma 1 and sigma 2. So, your new alphabet is going to be the set of all symbols in the first alphabet union the set of all symbols available in the second alphabet. So, now to find out the various transitions, once again a string is going to be recognized either by the first automata m1 or by the second automata m2. If you want to recognize the string by the first automata, then we need all the transitions from del 1. If it is going to be done by the second automata, we need all the transitions from del 2. So, every transition from del 1 and every transition from del 2 must be there in your del, that is nothing but the transition for your new automata. So, we have del 1 union del 2, but that itself is not sufficient, because we go for a new state, that is q, that is nothing but the starting state of the new automata. As far as the new automata is concerned, every transition must start only from the new starting state, that is going to be your q. So, obviously there should be transitions from q for either the starting state of the first automata or the starting state of the second automata. So, if you want to recognize a string by the first automata, you make a transition from, that is your q to q1 without consuming any input symbol. So, that is very important. If you are consuming some symbol just for making a move from q to q1, then the language is going to be a different one. But we wanted to have only a union language. So, you start from q, do not consume any symbol, jump to q1, or start from q, do not consume any symbol, jump to q2. So, the q1 is made as the destination state if the string is to be recognized by the first automata, and the q2 is going to be made as second state if the string is going to be recognized by the second automata. So, automatically you can start from q and we will be able to jump to q1 or q2 depending upon the string which we want to be recognized. Then finally, after recognizing the string either by the first automata or by the second automata, we will be reaching the corresponding final states. It means that we can construct an automata for the union of two automata. So, the union property is going to be accepted by the closure, that is your regular languages. The next property here we are having is the complementation. See, first you should understand what is the meaning of the complement. A string is there, suppose if you are having a string that is x which is available in a language, then as far as the complement is concerned, then x is not going to be there. So, every string available in the language, given language L, should not be available in the complemented language. So, if you are able to construct the language that is your L for which there exists a finite automata, then is it possible to construct an automata for the complement of L, so that we will be able to recognize only the strings which are not available in the language that is L. So, if such an automata is existing, then we can say that the complement is also going to be a property accepted by regular languages. So, the simple idea for that is, you construct first of all the automata for the language that is L, and once the construction is over, we know that there will be a set of final states and there will be a starting state. So, if you are starting from the first state, that is your starting state of the automata, and if you can reach the final state of the automata, it means that the string is in the language of the automata. If you are starting from the starting state of the automata, and if you can't reach the final state for some string that is x, then it is not going to be there. So, now we have to recognize, that is, if you are constructing the automata for the complement of the language, we have to recognize the set of all strings for which it is not possible to reach the final state from the starting state, but these are the strings we want to recognize by the complemented automata. So, what we should do for that is simply invert the final states and non-final states. Every final state available in the given automata should be made as non-final state for the resulting automata, and every non-final state should be made as the final state. So, what will happen is, a string is going to be accepted if it is reaching the new final state. The new final state is nothing but the one which is going to be the that is non-final state of the given automata. So, that construction here we can see, that is, first you are given an automata that is M, which is going to be q, sigma, del, q naught and f. These are all the various components as far as your finite automata is concerned, and the condition is the language is going to be L, which is going to be accepted by the automata M. Now, we are going for the construction of a new automata for the complemented language. All the components available in M are used here, that is, q is used as such, even sigma is also used as such, del no modification, the starting state no modification, but only the change available here is with respect to the set of final states. So, f is going to be the set of final states in the given automata. As far as the complemented automata is concerned, every state which is not there in f will be in the f for new automata. That is, q minus f is going to be the expression that is going to tell you what is going to be the set of final states for the new automata. That is, every non-accepting state of M are made as the accepting state for N, and the reverse, every accepting state will become the non-accepting state for that. So, now to prove that this is going to be the complemented automata, so we can say that W is in the language of the non-deterministic finite automata, or the finite automata which is constructed for the complemented language, if and only if del of q naught comma w is in q minus f, which occurs if and only if w is not in L of M. So, that is the idea behind the construction of the automata. So, how we are recognizing the set of all strings in the complement automata is described here. A string w is in L of n if and only if del of q naught comma w is in q minus f, and it is going to occur if and only if w is not in L of M. So, a very important point here we have to remember for the construction of the complement automata is, first of all, we must ensure that from every state we will be having transition for every symbol available in the alphabet. Suppose if you are having a state that is qi, and the alphabet includes both a and b as symbols, then from qi we must have a transition to, that is, for a as well as for b. So, but if you find that the transitions are all defined, then when you go for the complement automata, from every state once again we will be able to find out the strings definitely which are not available in the complemented language. Suppose if it is not satisfied, that means from every state if you do not have transitions for every symbol available in the alphabet, how do we handle the situation? So, for that first of all we should create some number of dead states. That is, if I find that from the state there is qi, I have only transition for A but not for B, then you must define a transition from qi for the symbol B which is going for a state which is dead. So, now that becomes a new state from where no transitions are defined. So, the condition is once again is applicable for the state that is which is introduced as a dead state also. So, how do you call it as, or how do you make it as a state with all transitions? For every symbol available in the alphabet, you make a transition from that state coming back to the same state. So, a state is said to be dead if it is not forming part of the path from the start to the final state. Since this is a state for which the transitions are defined to itself, it is not possible to move from this state to the final state of the automata once we have reached that particular state. So, this is what we have to do even before going for the complementation. But once this condition is satisfied by all the automata available in the given that is automata, all the states available in the given automata, then we can go for the formulation whatever we have described earlier. That is, you will be having some number of final states and some number of non-final states. Every dead state we have introduced in the automata are becoming the non-final states as far as the given automata is concerned, but after complementation they are all becoming the final states. So, a string, if it is possible or if it is recognized by reaching the dead state, it is there in the complement of the language, but it is not there in the original language. So, that is the idea behind the construction of the complemented languages. Let us see that is how we are constructing it for the union of difference among the or the intersection of the languages. It is once again a binary operation. We are having the languages L1 and L2, we are having automata that is Q1, that is sigma 1, del 1, Q1 and F1, this is going to be second automata, and the difference or your intersection is defined by the cross product. First of all, you will define the states Q1 cross Q2 and a state from Q1, a state from Q2. The starting state is the starting state of the first automata followed by the starting state of the second automata, and the final state is one final state from the first automata and any one final state from the second automata. So, you are always processing the states in pairs. So, every time when you are taking a transition, how it is defined? It is a pair of states p comma q is defined as the input state for your del with an alphabet their symbol that is a. So, now to find out the set of states, so what should be done is from p for the input symbol a, what the output produced by your del 1. So, you are having del 1 of p comma a, that is the first output, then from q what is the output produced for a, that is for the second automata. So, it is going to be del 1 of p comma a followed by del 2 of q comma a. So, what will be the output? Maybe it is r and s. So, if it is going to be r and s, that is going to be a state available in the new automata, and suppose if r is a state from f1 and s is a state from f2, then we can say that we have reached the final state of the automata. So, for the construction of the intersection, select the automata, first you form the states as far as your there is the language alphabet is concerned. Any string is going to be there in the intersection of the language L1 and language of L2 only if it is there in both L1 and L2. So, it is enough to take only the strings with the alphabet containing symbols from both sigma 1 and sigma 2. So, even for the construction of the alphabet, it is enough to go for that is sigma 1 intersection sigma 2. Then for the final state, just take the cross product such that both the states available in the pair are from the final states of first one and the final state of the second one. So, this is how we can form even the automata for intersection also. Since we can form an automata for the intersection, it is possible, or you can say that the intersection of two regular languages is also going to be the regular language. To summarize, we have seen that as the various closure properties of the regular languages. It is going to be the union, intersection, complement, even reversal. Reversal we can start from the final state and you can go to the starting state, but the starting state should be that is your unique, but as far as the final states are concerned, it can be even there is more. So, we will make a common final starting state and we will make some non-deterministic transitions to the final states. Now, we can make the common final state as the new starting state. So, reversal could also be done. As far as the problem point of view is concerned, we can have that is questions like proving the properties of reversal or complement or difference or even union or intersection. So, anything may be that is asked. So, you have to take particular that is automata, even if it is, suppose if it is going to be unary operation, only one automata is sufficient. If it is more, then more number of automata must be taken and construct the new automata, prove the language is going to be the or the property is going to be accepted by regular languages. So, that is all from this lecture. Thank you all.